Stand up for a moment. Do not walk yet. Just feel what your body is doing. Your spine balances over your hips, your knees lock beneath you, your feet spread your weight across the ground. It feels automatic, but it is one of the strangest things any ape has ever done. Most mammals carry their bodies on 4 limbs. Your ancestors eventually trusted only 2. That choice changed everything. It freed the hands, altered the pelvis. It reshaped the spine. It even changed how babies entered the world. So why did it happen? The old answer sounds simple. Africa became dry. Forests shrank. Climbed down. Then they stood up to cross open grassland. A taller body could see predators. 2 legs could travel farther. Free hands could carry food and tools. That's how it appeared in textbooks for generations. It is neat. It is visual. It is also probably incomplete, because the oldest clues do not show a fully ground-dwelling walker. They show something much stranger. An ape that could stand upright, then climb straight back into a tree. The story begins around 7 million years ago. That is close to the estimated split between the human and chimpanzee lineages. In northern Chad, researchers recovered fossils of Sahelanthropus chidensis. The species became famous for its skull, but one damaged thigh bone mattered even more. In 2022, Guillaume Daver and colleagues published a detailed analysis in Nature. They examined 1 femur and 2 forearm bones. A femur is the large bone inside your thigh. The femur showed features most consistent with habitual bipedalism. Habitual means this was not a rare party trick. Walking upright was probably part of normal movement. But the forearm bones told another story. They preserved signs of powerful climbing. Same animal, same body, 2 very different worlds. The ground mattered. The trees still mattered too. That combination is the first crack in the classic savanna story. If open grassland alone created bipedalism, the earliest walkers should look increasingly built for the ground. Sahelanthropus does not. It looks like a climber experimenting with upright movement. And it was not alone. Around 6 million years ago, another species lived in what is now Kenya. Its name was Ornithugenensis. In 2013, Sergio Almasija and colleagues analyzed the shape of its upper femur. They published their work in Nature Communications. The bone did not look exactly human. It did not look exactly like a modern ape either. It occupied an intermediate position. That word matters. Intermediate does not mean unfinished. Evolution does not build toward a target. It preserves whatever works. Orwin may have combined climbing with some form of upright walking. Again, 2 legs did not replace the trees. 2 legs worked beside them. Then comes Arti. Ardipithecus ramidus lived about 4.4 million years ago in Ethiopia. In 2009, Tim White and a large international team published the major description in Science. Arti had a grasping big toe. That means the foot could still grip branches. But the pelvis and other parts of the skeleton suggested upright movement on the ground. This was not a modern human walker. Her feet were different. Her balance was different. Her stride was probably different. Yet she was not a knuckle-walking chimpanzee either. Arti represented another mosaic. A mosaic is a body built from traits that look surprisingly mixed. Some helped in trees. Some helped on the ground. Some belonged to neither modern humans nor modern apes. And the environment around Arti made the mystery deeper. White and colleagues argued that Arti lived in a largely woodland setting. Other researchers later debated exactly how wooded it was. But almost nobody describes it as empty grassland. There were trees, there were patches of cover, there were climbing opportunities. Bipedalism had not waited for a treeless world. That creates a new question. What if standing upright did not begin after your ancestors left the trees? What if it began inside them? Picture a large ape on a flexible branch. Fruit hangs beyond easy reach. The branch bends under its weight. Moving on all fours keeps the body low. But it also occupies every limb. Now the ape rises. One hand grips an overhead branch. The feet balance on another. The free hand reaches toward food. For a few seconds, upright posture becomes useful. Not because the ape is crossing a plane, because the ape is feeding. This is called postural feeding. a technical phrase for standing or balancing to reach food. The behavior still appears in living apes. Chimpanzees sometimes rise on two legs. Orangutans use upright positions of your ancestors. Modern apes are not frozen versions of your ancestors, but their behavior can reveal what an ape body is capable of doing. A 2022 study made that possibility harder to ignore. Rihanna Drummond-Clark and colleagues observed wild chimpanzees in Tanzania's Isa Valley. The study appeared in Science Advances. Isa is a savanna mosaic habitat. That means woodland, grassland, and forest appear together. The team wanted to test if more open habitat should push apes onto the ground. More time on the ground should produce more upright behavior there. That is not what they found. The Isa chimpanzees spent as much time in trees as chimpanzees in more forested habitats. Their bipedal behavior happened mainly in trees. Most of it was linked to feeding. The open environment had valuable trees more important. And once inside those trees, upright posture helped them reach food. This does not prove your ancestors evolved bipedalism the same way. Living chimpanzees are not ancestral humans. One population cannot recreate 7 million years. But the study destroys one lazy assumption. Open habitats do not automatically make apes abandon trees. Sometimes fewer trees make each tree more valuable. That is the twist. Your first upright steps may not have been long marches across the savanna. They may have been careful movements on branches, 2 feet below, one hand above, the other reaching for fruit. Walking came later. Standing may have come first. The fossil record shows that transition becoming clearer over time. At Laetoli in Tanzania, volcanic ash preserved a remarkable trail. The footprints are about 3.66 million years old. In 2016, Fidelis Masao and colleagues described additional tracks at the site in eLife. The prints belong to bipedal hominins moving across the same ancient surface. Their big toes is aligned with the other toes. Their feet no longer worked like grasping hands. They stepped with a heel-first motion, then pushed forward through the toes. That is recognizably human-like walking, not identical to yours, but far closer. By then, upright locomotion had become more committed. The foot had sacrificed some climbing power. The ground was becoming home. Yet even Australopithecus afarensis retained climbing-related features. Lucy belonged to that species. Her kind walked upright. But shoulders, arms, and curved finger bones still hint at life above the ground. The transition did not happen once. It unfolded in stages. First, upright posture may have helped with balance and feeding. Then short bouts of two-legged movement became more common. Later, changes in the pelvis, thigh, knee, spine, and foot made walking more efficient. Different pressures probably acted at different times. Food mattered, energy mattered, heat mattered, visibility mattered, carrying mattered. No single idea needs to explain every stage. Evolution rarely has one reason. It stacks small advantages: a slightly better reach, a slightly safer balance, a slightly cheaper step, a slightly easier way to carry food. Each advantage matters only in its own environment. Then environments change. The old trait finds a new purpose. This is called exaptation, a fancy word for a feature reused for another job. Feathers may have helped control temperature before flight. Upright posture may have helped in trees before long-distance walking. Once your ancestors spent more time on the ground, the old posture became a new locomotor system. The body then paid a price. Your lower back curves inward. That helps balance the torso above the hips. It also creates weak points. Your knees angle beneath your center of mass. That stabilizes each step. It also places stress on the joints. Your pelvis became shorter and broader. That supports upright walking. It also complicated childbirth. Your feet developed arches. Those arches store energy like springs. They also lost much of their grasping ability. You gained an efficient walking machine. You lost an extra pair of hands. That trade changed what your ancestors could become. The change also transformed distance. A chimpanzee can walk upright for short stretches, but the movement is costly and unstable. Human walking is different. Your hips keep the pelvis from dropping with every step. Your long legs act like pendulums. Your arches return some energy to the next stride. That economy became powerful once food and water were scattered. A body that spent less energy per kilometer could search farther. It could return with more. It could survive leaner seasons. But this was probably a later reward. Efficiency explains why bipedalism became increasingly specialized. It does not fully explain the first upright moments. Those moments happened in bodies that still climbed well. That distinction separates origin from refinement. The first advantage starts a behavior. Later advantages reshape it. Confusing those stages creates the illusion of one perfect cause. There was probably no perfect cause. There was only a chain of useful accidents. Free hands could carry infants. They could transport food. They could shape tools. They could gesture. But hands were not necessarily freed because tools already existed. The earliest secure stone tools are far younger than the first evidence for upright walking. Bipedalism came first. The famous hands came later. That sequence matters. Your ancestors did not stand up because they were already becoming human. Standing up helped create the conditions that made later humanity possible. Yet even that sounds too clean. No ape woke up and chose 2 legs. No generation crossed a clear border. A mother climbed differently from her parents. A juvenile balanced slightly longer. A population used open branches more often. Bones changed over thousands of generations. Muscles shifted, feet stiffened, pelves widened. Eventually, a movement that once lasted seconds became the default. You can feel that history right now. Stand still again. Notice the tiny movements in your ankles. Your body is never truly motionless. Muscles constantly correct your balance. Your brain performs the calculation without asking permission. That system is ancient, but it is not perfect. You were built from compromise. A climber became a walker became a runner began sitting in chairs. Now your body carries 7 million years of experiments into a world of elevators and screens. That is why the question has no single answer. Your ancestors walked on 2 legs because upright posture kept solving new problems. First in mixed habitats, possibly in branches, then on the ground, then across longer distances. The advantage changed. The body followed. The simple savanna story imagined a dramatic exit. Trees behind, grass land ahead, but evolution usually looks messier. Your ancestors did not leave one world and enter another. For millions of years, they belonged to both. They climbed, they stood, they reached, they walked. And every step you take still carries the memory of a branch beneath your feet.